Astronomers make a seemingly unbelievable claim, which is that the ordinary form of matter that makes up you and me is just a small fraction of the energy budget of the universe. They claim that there's another form of matter, called dark matter, that is 5 times more common than the familiar form. So what is the nature of dark matter, and how will we find it? That's an interesting question, and I think it's worth taking some time to look into it. If dark matter is so much more prevalent than ordinary matter, surely it must be easy to find, right? I mean, after all, we can see stars and galaxies, so what's the problem? The problem is that dark matter is, well, dark. It doesn't emit or absorb light. That makes it hard to detect by any manner other than its gravitational effect on the familiar form of matter we can see. And that's why we believe dark matter exists. Galaxies rotate faster than the observed ordinary matter can explain using the known laws of physics. Ditto with the motion of individual galaxies inside clusters of galaxies. And the images of distant galaxies are distorted more than can be explained by the effects of ordinary matter between the distant galaxies and our telescopes. All of these are reasons why astronomers believe that dark matter is real. But just what is dark matter? It might surprise you that scientists just simply don't know. It could be a gas of unknown subatomic particles with a mass much lower than the mass of electrons, or it could be made up of objects as heavy as stars. If you want numbers, the possible range starts with a mass of about 10 to the minus 6 electron volts on the low end, or about 10 to the minus 71 solar masses, up to a mass of about 1,000 solar masses on the high end. That's a ridiculously large range, with the difference from smallest to largest about 10 to the 75th power. It wouldn't be unreasonable for someone to hear that and conclude that scientists don't have a clue about the mass of individual dark matter particles. That's, of course, not the whole story. After all, scientists have been looking for dark matter for many decades, and some possibilities have been ruled out. For instance, astronomers have used telescopes to look for types of dark matter in the mass range of asteroids, moons, planets, and stars. Well, the dark matter can't be seen. After all, it's dark. If a dark matter star passes in front of another star, you can detect its passage. Using this technique, astronomers ruled out forms of dark matter in the 10 to minus 7 times the mass of the Sun to about 30 times the mass of the Sun. That's about the mass of Mercury to 30 solar masses, give or take. We can actually rule out all candidate forms of dark matter made from non-glowing versions of ordinary matter, like gas, asteroids, planets, etc., simply because they wouldn't be dark. They'd heat up from the light of surrounding stars and emit infrared light, so we can rule out that form of dark matter. Now, for a very long time, most of my career, actually, scientists have hypothesized another form of dark matter, what are called WIMPs, short for weakly interacting massive particles. WIMPs are thought to be subatomic particles, kind of like heavy and stable neutrons. The hypothesized mass range was somewhere from slightly lighter than a neutron to maybe 10,000 times heavier. And scientists have looked for versions of this type of possible dark matter. And, in spite of decades of looking and huge improvements in detector sensitivity, researchers have found absolutely nothing. Now, that doesn't mean that dark matter in this mass range is ruled out. But it does mean that if it exists, it interacts very weakly, maybe only via gravity. And if dark matter interacts only via gravity, we may never see it. That would be annoying. However, we shouldn't be negative yet. Maybe dark matter interacts weakly with ordinary matter, but strongly enough that we can still find it. But that means looking in different places using different techniques. And that's what we're doing at Furmilab, in collaboration with a number of sister institutions. Rather than the traditional searches for WIMPs, researchers here are trying different and innovative approaches. Let me tell you about 2. Sub-electron noise Skipper CCD experimental instrument, or SENSE, uses ultra-low noise silicon charge couple devices to look for dark matter particles with a mass as low as the mass of an electron. That's 500,000 electron volts if dark matter scatters off electrons in the chip, and as little as a single electron volt if the dark matter gets absorbed by the electrons surrounding the silicon atoms. And this isn't just hypothetical. These super quiet electronic chips are astoundingly powerful for finding low-mass dark matter that interacts with electrons. A single sensei detector weighing just 2 grams outperforms a competing detector using liquid xenon with a mass of a ton. And the sensei experiment will be upgraded to a mass of 100 grams. Sensei is going to totally dominate searches for this form of possible low-mass dark matter. But of course, dark matter might not have the properties that Sensei is designed to detect. And given that astronomical measurements have ruled out a lot of very heavy options for dark matter, and the WIMP searches have ruled out a lot of possible heavier subatomic particles, we need to explore more thoroughly the very low-mass dark matter options. In 1977, physicists Roberto Pecci and Helen Quinn were trying to solve a mystery involving the strong nuclear force. According to the theory governing the behavior of quarks and gluons, the strong force could favor either matter or antimatter, but it seems to treat both equally. Pecci and Quinn proposed a new energy field that forced the strong force to react equally with matter and antimatter. If that energy field is true, this means that a new particle exists, one that we've never seen before. This particle is called an axion. Axions are very low mass, don't emit or absorb light, and, in short, are a perfect candidate for low-mass dark matter. Well, that is, if they exist. So Fermilab scientists are participating in a collaboration called ADMX, short for Axion Dark Matter Experiment. This experiment uses a very strong magnet and a cavity that resonates at a certain microwave frequency. It's a bit like when you blow across the top of a 2-liter bottle and it makes a sound of a specific frequency, except, of course, it's microwaves and not sound. The experiment depends on a quirk of axion theory, which says that in the presence of a strong magnetic field, an axion can convert into a microwave. It's a tiny effect, but the microwave cavity is surrounded by super powerful amplifiers that make it possible to see the conversion of an axion to a microwave. The ADMX experiment is designed to look for axions with a mass of about 3 millionths of an electron volt. This is at the bottom end of what scientists think is reasonable for dark matter. So far, they've found nothing. I think the real takeaway message is that scientists don't have a preconceived notion of what dark matter might be. I mean, we know that there are lots of astronomical observations that could be explained by dark matter, so we keep looking for it. But we've not found it, so we look in all possible places under all metaphorical rocks. The dark matter research community has looked for candidate particles from a millionth of an electron volt all the way up to much heavier than the sun, and we found nothing so far. That doesn't necessarily mean that dark matter doesn't exist. It might just have properties that current and past experiments weren't sensitive to. And of course, it might actually mean that dark matter isn't real and that we need another explanation for those astronomical observations. But we need an explanation, so I'm glad that my colleagues are looking so hard at possible answers. I'm impressed that the Sensei experiment, using a mere 2 grams of silicon, is more sensitive to certain measurements than much larger detectors. And I'm super glad that ADMX and similar experiments are looking for super light versions of dark matter. We wouldn't want to get tunnel vision looking for the WIMPs that the theoretical community favored for so long. No matter the answer, the questions of why galaxies rotate so fast and why the image of distant galaxies are so distorted are fascinating ones, and we won't understand the universe until we've answered them. Open questions are the most fascinating ones, and I hope we'll figure it out soon. Asking hard questions is what scientists do.